Hello everyone, welcome to this two-lecture series on deep dive into ESXi architecture. Now here is the agenda of this particular series where we will be discussing about ESX architecture and its limitations. Now folks who are new to VMware data center technology, they might not have heard about ESX product, but it is good to know a brief history about the ESX hypervisor product and its evolutions before we jump in and discuss about ESXi architecture. That is the reason we try to capture a brief history about ESX architecture and its underlying limitations. Then we'll discuss about three crucial components of this architecture, which is VMX, VMM, and VMK. So we will be discussing about these three crucial components of VMware hypervisor architecture. Then in part two of this series, we will be discussing about why ESXi, the reason behind why ESX got deprecated, and what are the architectural benefits of this next generation hypervisor, so-called ESXi. And then we'll discuss about installation requirements of this ESXi hypervisor. So with this agenda, let's get started. So that's how the topic, ESX architecture and its limitations. Now, this is a slide which talks about a brief evolution of various generations of VMware hypervisor. So if you look at that, the first server category product which was launched by VMware was back in 2001. So back in 2001, VMware launched a first server category product called GSX. Now this product was very short-lived product because of its architecture. If you look at this diagram clearly says that this GSX server was actually a type 2 hypervisor, or we call it as a hosted architecture, because the server hypervisor layer or the hypervisor layer of VMware was sitting on a general purpose operating system. It could be Windows or it could be Linux operating system. And because of this general purpose operating system dependency, this architecture could not be a enterprise grade level architecture. And that was the reason this server product was very short-lived product. And very soon, back in 2003, VMware launched a new enterprise grade architecture, which is ESX, or we call it as a type 1 hypervisor. And as you could see that your server hypervisor or VMware hypervisor layer was sitting right on top of the bare metal hardware. So there was no dependency on any general purpose operating system, and that was making this architecture as a server grade enterprise level architecture. Now, but there were some underlying issues with uh, this architecture also, and that is the reason back in 2007, VMware introduced another next generation of hypervisor, what we called as ESXi. And this is the ESXi, which is being continued from 2007 and it's to 2021. So this is the enterprise grade level architecture, which actually VMware is continuing with uh, a decade. So we'll discuss about what is ESX and what is ESXi architecture and what are the underlying differences between these two architecture. And that's the whole agenda of this particular lecture. So with that, let's get started. Now, this is the slide which actually talks about the ESX architecture. Now you could see a lot of components in this architecture. So let's try to simplify this architecture from our understanding perspective. So let's start from the bottom. So on the bottom, you could see that we have a hardware. So this is your hardware, like your CPU, memory, hard drive, network adapter. So this is your bare metal hardware or your bare metal server, which is having this particular hardware devices installed. Now, this big orange color, what you see it here, this orange color is basically, this is our ESX server. And this is what we call it as a VM kernel. So as you might be knowing that every operating system has a kernel, and that kernel is considered to be heart of any operating system. Similarly, in the case of VMware hypervisor, this kernel is called as a VM kernel. Now, the layer what you see here, which is named as VM kernel hardware interface layer. Now, this is the interface layer. This is a driver module which actually provides a support to a large hardware ecosystem or vendor ecosystem. So this is the interface layer, which is actually a VMK Linux driver. And that driver was designed to provide a communication between VM kernel and the Linux driver. Now, because of this layer, VMware was having a big hardware ecosystem, and it was supporting a wide variety of hardware devices. But the only issue with this interface layer was it was another layer of emulation, which actually having a implication on the performance. Then basically, if you see that in the 5.5 onwards, VMware actually introduced a native driver stack, and this particular interface layer is not required anymore because we don't require a translation layer which actually translates your VMkernel instructions into the vendor specific instructions because of the native driver stack support. So from 5.5 onwards, there is a support of native driver stack, which actually improves the overall kernel performance. And 6.7, I believe, is the last release where they were having a support of this hardware interface layer. And from 7.0 onwards, there is no hardware interface layer at all. It's completely deprecated by the VMware, and now they're just supporting a native driver stack for a improvised performance and faster boot process and optimization purpose. Now the next is basically what do we have? Device drivers. So device driver, as we know that every hardware would have a device driver sitting in the kernel, right? Because kernel will not be able to claim the device until unless there is a driver installed in the kernel. So that's what device driver is all about. Then you could see that we have a storage stack and network stack. So storage stack is basically taking care of all of your storage requirements, like your VMFS, your all this SCSI request processing is being handled by your storage stack, which is again running in your VM kernel. And then you have a network stack, which is a typical TCP/IP stack, which is again running in our ESXi kernel and giving us a capability, virtual networking capabilities like virtual switching, forwarding, and filtering. Now on the other side, as you could see that we have a resource management, and that's the MMU unit, memory management unit, or we have all the scheduler, your CPU, memory, network scheduler. They used to sit or they sit in this VM kernel, and they takes care of all the scheduling requirements in terms of CPU, memory, or network and storage. Now, in this kernel or in this architecture, you might have noticed that we are running 4 VMs. So this is a Red Hat VM, this is a SUSE VM or Novel VM, and then we have a 2 Windows VM, right? So one of the things which I want you to have attention on, as you could see that every VM will have a 2 components respectively. The first component, we are seeing it as a VMM. So we have a 4 VMs, and similarly we have a 4 VMM components. And on the other side, as you could see that we have a 4 VMX component, which means for every VM, there would be one VMX and one VMM component associated with it. Now there's a reason what is VMX, what is VMM. We're going to discuss about these two particular critical component of the ESX architecture. So just hold on to that. But remember that every single VM will have a one VMX and one VMM component. Now, VMM stands for virtual machine monitor, where VMX stands for virtual machine executable. Now, what I would like to focus you on looking at this big chunk, what we calling it as a service console. Now, in the ESX architecture, when VMware introduced, they had introduced a service console. Now, this service console is nothing. It's a Linux kernel, which VMware integrated with their hypervisor code to serve a specific services or task like a bootstrapping of hypervisor layer, giving us some kind of management functionality or giving us some kind of administrative or management interface. So all these capabilities were actually not being served by a core hypervisor code, but those capabilities were actually being offered by another third-party Linux kernel, which we used to call it as a service console. So in the ESX architecture, it was a combination of VMware proprietary kernel code, which was giving us all the native capabilities of hypervisor layer, but they were also having a big fat component called service console, which was a which was a Linux kernel, and that kernel was actually providing us a couple of services or a couple of things like a management functionality, administrative or management interface, and bootstrapping of our hypervisor layer. So as you could see that this service console was having its own device drivers. It was having its own network stack. So what the network stack you do see in this kernel layer, it's different than the network stack which is present in the service console, because this network stack or IO stack was coming from a Linux kernel. So this service console was having its own device driver, its own IO stack. And as you could see that all of the management agents, whether we talk about like VPXA, HostD, SNMP, all these management agents or third-party agents were sitting in this service console. And that was the whole idea of this service console, to have it. Now, that's how your entire ESX architecture looks like. And on the other side, you could see that we had a vCenter server which used to manage our ESX host, just like what we have in the ESXi. And this vCenter server was giving us a lot of distributed services like vMotion provisioning and a lot of other distributed services. So that's the pretty much about the ESX architecture. Now let's talk about the drawback of this architecture. Now the service console which we discussed about, this service console was, as we discussed, based on the Linux kernel, because those days VMware was not having their own native interface for management or troubleshooting or administrative purpose. So they actually took up a Linux kernel and they integrated that kernel into their hypervisor code, and they call that product as a ESX product. And that service console was actually used to boot a hypervisor layer and also used to provide us administrative for troubleshooting. So I still remember during early those days back in 2004 time frame, the CSX kernel used to familiar as it used to look like your typical Red Hat kernel. Every single command what you could run it on the Red Hat kernel or Red Hat operating system, you could run those commands exactly on the ESX kernel, and that was really easy to get familiar with this new hypervisor layer. Now, because of this service console and because of this Linux kernel, the code footprint was really big. And this ESX architecture code footprint was around 2 GB. So if you wanted to install this ESX hypervisor, you will have to download this image, then will have to burn this image into some CD-ROM, CD drive and DVD drive, because that was a very large footprint of 2 GB code. And then we used to have an installer like Anaconda installer through which we gonna do the installation. The installation procedure of this ESX architecture was exactly same as your Red Hat installer, because they were using the same Anaconda installer for the ESX installation as well. Now, because as we know that as an industry standard, if your code footprint footprint is larger, or it means that product is more vulnerable to attack, because because of a larger footprint, it has a larger surface to attack, and that was the reason this product was less secure and more vulnerable to attack. Now, another problem with this particular architecture was it's other than its bigger footprint and less security or less secure in reliability, but the other issue was that console OS, the service console, and that service console was heavily loaded with VMware agents, um, and that used to provide another layer of context switching, and which used to impact overall system performance. So that was another issue with this particular architecture because hardware. So there's another layer which got introduced in the IO path, which used to impact the system performance. And as we discussed, a lot of management functionality, management agents, third-party agents were running natively in this console operating system, making that console operating system is really bottleneck from the architectural perspective. And another issue was that user has to log into the console operating system in order to run commands for any kind of diagnostic and troubleshooting purpose. So if you look at this particular architecture now, because if you want to do any kind of troubleshooting, you need to have a console access to that operating system, and that console access was used to provide by this service console. And VMkernel was not having any native console operating system at that moment, so you had a complete dependency on this service console. The other issue with that, this ESX was not having a dual boot bank implementation, which used to make upgrade as a really painful from the customer perspective, because if during the upgrade anything goes wrong, there was no simplified way or easiest way to roll back to the previous working image. So that was another issue with this architecture. And one of the most important and the last issue with this architecture was patching the the ESX architecture, the ESX product. As we know that patching a data center has always been a very complicated and difficult task, right? Now, because this ESX architecture was integrated with a, a third party, Red Hat or Linux kernel. So now imagine a scenario, there is no bug in the ESX proprietary code, or there is no bug in the VMware proprietary code, which actually serving a 90% of the functionalities of the hypervisor. But any bug which introduced in Linux kernel, the VMware has to release a new patch of the entire ESX hypervisor image, and customer has to upgrade their data center. That was another big drawback of this ESX architecture. So these are the couple of points because of which this ESX architecture, though it was an enterprise grade architecture, but because of this the way it was designed, the way it was architect, there was an issue which got addressed in the next generation of hypervisor, what we called as a ESXi. Now, before discussing on the ESXi, let's go and discuss about a very crucial component of this hypervisor architecture, which is our next topic, VMX, VMM, and VMK. So let's talk about what is VMX. So as you could see that in this particular diagram, we have a VMs. So we have a 4 VMs running their own applications and operating system. But if you notice that every VM will have a associated VMM and associated VMX. So what is this VMX? VMX stands for Virtual Machine Executable. Now, this VMX is a user level application that does a couple of things. The first, bootstrapping, and it also does the emulation for devices which are not so critical uh, to kernel performance, such as your input output devices like your keyboard, mouse, or any devices which are not critical to the performance. It provides that kind of emulation for those particular devices. Now, this VMX also holds application infrastructure activities. So a couple of other activities also being held by this particular application, such as communicating with the UI, hostd. So you might have known that whenever we do any operation on the ESX kernel, the hostd is the one which actually go and perform the required set of operations, right? But VMX is the one which actually go and provide this kind of infrastructure where it provides a communication with the UI, with the ESX UI and hostd daemon and remote display, snapshots, so forth. So VMX is one of the very critical component of this ESX hypervisor architecture. Now the next component is VMM. Now what is VMM? A VMM is again a software component that comes as a part of your ESXi or ESX hypervisor. Now this software component is actually implements another abstraction layer, and that abstraction layer it implements for virtual machine hardware. So the way our VM kernel manages our physical hardware resources, similarly this VMM component manages the virtual machine hardware associated with that specific VM. Now this VMM is also responsible for CPU virtualization and emulation of critical IO devices. So whenever we have a critical IO devices, for example, CPU, any instruction which has to be scheduled on our on CPU or memory instructions. So those kind of IO devices or those kind of instructions are get virtualized by this VMM software component of this entire architecture. Now this VMM actually works as an interface between our guest operating system and our VM kernel. So any request which is coming from the guest operating system will be trapped by that VMM or will be accepted by that VMM component of that operating system. And then this VMM will go and talk to the VM kernel for the required set of instructions or required set of uh, execution. So you could see that a VMM is the responsible component of this hypervisor architecture to serve the best of the best services to our virtual machine. So VMM pass the request from virtual machine and then it pass it to the kernel. The VMM runs directly in privilege mode on the native CPUs and it cooperated with the VM kernel as we discussed. For example, let's say if you created a VM which requires some kind of memory. For example, it requires a 2 GB of memory. So now what will happen, that request of 2 GB memory will be taken by the VMM component associated with that VM, and that VMM component will go and talk to the VM kernel and request that VM kernel to provide a 2 GB of memory pages. So that's what the job of the VMM is. Now each VMM is per VM and has one vCPU thread per vCPU, which means that there is a one-to-one mapping between vCPU of the VM and VMM component. So if your virtual machine is having a two vCPUs, there would be a two threads of VMM component, right? Because every VM has a association with the respective vCPU assigned to that vCPU thread assigned to that particular VM. Now this VMM component implements virtualization of guest OS instruction sets, MMU, and other VM hardware. So this is another, as we discussed, another virtual machine hardware abstraction layer, which works and takes care of the guest operating system virtualization. Now the next is VM kernel. So what is VM kernel? The VM kernel is the operating system that is the core of the ESXi or ESX hypervisor. This VM kernel handles resource scheduling and device IO like any other kernel of any other operating system. The VM kernel does the same job, where it actually manages your resources and handle the device IO. Now, this VM kernel software is responsible for hosting and managing your virtual machine. So this VM kernel is actually responsible for creating your virtual machine, hosting your virtual machines, and managing your virtual machines. It runs directly on the hardware. As we discussed, this is a type 1 hypervisor, and this VM kernel hypervisor sits or get installed directly on top of your underlying bare metal hardware. Now, this VM kernel layer, it serves as a layer between your network and storage stack and your device driver. So as you could see that you have a network and storage stack, and you have a device drivers, your respective network adapters, your respective storage devices. And this particular VM kernel layer, it serves as an interface between your storage network stack and uh, your device driver, which handles this particular devices. So all the device IO is being handled by your network and storage stack. So that's what pretty much about your VM kernel. So now this is what we have discussed in this particular lecture 1. And in lecture 2, stay tuned for our lecture 2, where we will be discussing about the ESXi architecture and its benefits. We'll discuss why VMware deprecated ESX architecture and they come up with the ESXi architecture back in 2007, and what are the underlying architectural benefits of ESXi, which was never there in the ESX architecture. And then we'll discuss about ESXi installation requirements. So we hope you enjoyed this lecture. Thanks for your time. Please like, share, and subscribe to our YouTube channel. Thank you.